To summarize, the periodic table is important because it is organized to provide a great deal of information about elements and how they relate to one another in one easy-to-use reference. The table can be used to predict the properties of elements, even those that have not yet been discovered. The table can be used to predict the properties of elements, even those that have not yet been discovered. Columns, groups, and rows, periods, indicate elements that share similar characteristics. The table makes trends in element properties apparent and easy to understand. The table provides important information used to balance chemical equations. The periodic table has gone through many changes since Dmitry Mendeleev drew up its original design in 1869, yet both the first table and the modern periodic table are important for the same reason. The periodic table organizes elements according to similar properties, so you can tell the characteristics of an element just by looking at its location on the table. Before all naturally occurring elements were discovered, the periodic table was used to predict the chemical and physical properties of elements in the gaps on the table. Today, the table can be used to predict properties of elements yet to be discovered, although these new elements are all highly radioactive and break down into more familiar elements almost instantly. Now, the table is useful for modern students and scientists because it helps predict the types of chemical reactions that a particular element is likely to participate in. Rather than memorizing facts and figures for each element, students and scientists need only glance at the table to learn much about the reactivity of an element, whether it is likely to conduct electricity, whether it is hard or soft, and many other characteristics. Elements in the same column as one other are known as groups, and they share similar properties. For example, the elements in the first column, the alkali metals, are all metals that usually carry a 1+ charge in reactions, react vigorously with water, and combine readily with nonmetals. Elements in the same row as one other are known as periods, and they share the same highest unexcited electron energy level. Another useful feature of the periodic table is that most tables provide all the information you need to balance chemical reactions at a glance. The table tells each element's atomic number and usually its atomic weight. The typical charge of an element is indicated by its group. Now, with the help of a square, we can design the periodic table of elements. How to teach the history of the periodic table. Dmitry Mendeleev's periodic table is truly iconic. In the 150 years since its conception, it has become the chemistry equivalent of the alphabet. While getting students to memorize the elements by rote is unhelpful, although there's always a couple of students who think that memorizing it makes them master chemists, understanding how the period table is structured is one of the most important concepts that they'll learn in our labs. Weaving the human stories behind the periodic table into our teaching can help with this. Hearing tales of the early attempts at constructing a periodic table in the 1860s, and about the endeavors of those smashing atoms together today in the quest to extend the periodic table, will also give students an appreciation of how science really works. What students need to know. Chemists have been trying to order the elements since they were first discovered. Patterns in the periodic table help chemists to predict properties of elements. The periodic table is a live document, updated and improved as new discoveries are made and evidence found. There are parallels in the development of the periodic table and the development of our understanding of the atom. Scientific ideas can change, models are modified as new evidence is found. Ideas for your classroom. Take your students back in time to the 1860s and give them some of the information about the elements that the mid-19th century chemists would have had access to. Ask them to use this to arrange and organize the elements into a logical grid structure. How do your students choose to group the elements? How are they ordering them? What does their table look like? The periodic table of chemical elements, often called the periodic table, organizes all discovered chemical elements in rows, called periods, and columns, called groups, according to increasing atomic number. Scientists use the periodic table to quickly refer to information about an element, like atomic mass and chemical symbol. The periodic table's arrangement also allows scientists to discern trends in element properties, including electronegativity, ionization energy, and atomic radius. Many scientists worked on the problem of organizing the elements, but Dmitry Mendeleev published his first version of the periodic table in 1869, and is most often credited as its inventor. Since then, the periodic table has evolved to reflect over 150 years of scientific development and understanding in chemistry and physics. Today, with 118 known elements, it is widely regarded as one of the most significant achievements in science. Groups are numbered 1 to 18 from left to right. The elements in Group 1 are known as the alkali metals, those in Group 2 are the alkaline earth metals, those in 15 are the pnictogens, those in 16 are the chalcogons, those in 17 are the halogens, and those in 18 are the noble gases. How the periodic table of the elements is arranged. Scientists had a rudimentary understanding of the periodic table of the elements centuries ago. But in the late 19th century, Russian chemist Dmitry Mendeleev published his first attempt at grouping chemical elements according to their atomic weights. There were only about 60 elements known at the time, but Mendeleev realized that when the elements were organized by weight, certain types of elements occurred in regular intervals, or periods. Today, 150 years later, chemists officially recognize 118 elements, after the addition of 4 newcomers in 2016, and still use Mendeleev's periodic table of elements to organize them. The table starts with the simplest atom, hydrogen, and then organizes the rest of the elements by atomic number, which is the number of protons each contains. With a handful of exceptions, the order of the elements corresponds with the increasing mass of each atom. The table has 7 rows and 18 columns. Each row represents one period. The period number of an element indicates how many of its energy levels house electrons. Sodium, for instance, sits in the 3rd period, which means a sodium atom typically has electrons in the first 3 energy levels. Moving down the table, periods are longer because it takes more electrons to fill the larger and more complex outer levels. The columns of the table represent groups, or families, of elements. The elements in a group often look and behave similarly, because they have the same number of electrons in their outermost shell, the face they show to the world. Group 18 elements, on the far right side of the table, for example, have completely full outer shells and rarely participate in chemical reactions. Elements are typically classified as either a metal or nonmetal, but the dividing line between the two is fuzzy. Metal elements are usually good conductors of electricity and heat. The subgroups within the metals are based on the similar characteristics and chemical properties of these collections. Our description of the periodic table uses commonly accepted groupings of elements, according to the Los Alamos National Laboratory. Alkali metals. The alkali metals make up most of Group 1, the table's first column. Shiny and soft enough to cut with a knife, these metals start with lithium, Li, and end with francium, Fr. They are also extremely reactive and will burst into flame or even explode on contact with water, so chemists store them in oils or inert gases. Hydrogen, with its single electron, also lives in Group 1, but the gas is considered a nonmetal. Alkaline earth metals. The alkaline earth metals make up Group 2 of the periodic table, from beryllium, B, through radium, Ra. Each of these elements has 2 electrons in its outermost energy level, which makes the alkaline earths reactive enough that they're rarely found alone in nature. but they're not as reactive as the alkali metals. Their chemical reactions typically occur more slowly and produce less heat compared to the alkali metals. Lanthanides, the third group is much too long to fit into the third column, so it is broken out and flipped sideways to become the top row of the island that floats at the bottom of the table. This is the lanthanides, elements 57 through 71 lanthanum, La, to lutetium, Lu. The elements in this group have a silvery white color and tarnish on contact with air. Actinides, the actinides line the bottom row of the island and comprise elements 89, actinium, Ac, through 103, lawrencium, Lr. Of these elements, only thorium, Th, and uranium, U, occur naturally on Earth in substantial amounts. All are radioactive. The actinides and the lanthanides together form a group called the inner transition metals. Transition metals, returning to the main body of the table, the remainder of groups 3 through 12 represent the rest of the transition metals. Hard but malleable, shiny, and possessing good conductivity, these elements are what you typically think of when you hear the word metal. Many of the greatest hits of the metal world including gold, silver, iron, and platinum live here. Post-transition metals, ahead of the jump into the non-metal world, shared characteristics aren't neatly divided along vertical group lines. The post-transition metals are aluminum, Al, gallium, Ga, indium, In, thallium, Tl, tin, Sn, lead, Pb, and bismuth, Bi, and they span group 13 to group 17. These elements have some of the classic characteristics of the transition metals, but they tend to be softer and conduct more poorly than other transition metals. Many periodic tables will feature a bolded staircase line below the diagonal connecting boron with astatine. The post-transition metals cluster to the lower left of this line. Metalloids, the metalloids are boron, B, silicon, Si, germanium, Ge, arsenic, As, antimony, Sb, tellurium, Te, and polonium, Po. They form the staircase that represents the gradual transition from metals to nonmetals. These elements sometimes behave as semiconductors, B, Si, Ge, rather than as conductors. Metalloids are also called semimetals or poor metals. Nonmetals, everything else to the upper right of the staircase plus hydrogen, H, stranded way back in group 1 is a nonmetal. These include carbon, C, nitrogen, N, phosphorus, P, oxygen, O, sulfur, S, and selenium, Se. Halogens, the top 4 elements of group 17, from fluorine, F, through astatine, At, represent one of 2 subsets of the nonmetals. The halogens are quite chemically reactive and tend to pair up with alkali metals to produce various types of salt. The table salt in your kitchen, for example, is a marriage between the alkali metal sodium and the halogen chlorine. Noble gases, colorless, odorless, and almost completely non-reactive, the inert, or noble gases round out the table in group 18. Many chemists expect oganesson, previously designated ununoctium, one of the 4 newly named elements, to share these characteristics. However, because this element has a half-life measuring in the milliseconds, no one has been able to test it directly. Oganesson completes the 7th period of the periodic table, so if anyone manages to synthesize element 119, and the race to do so is already underway, it will loop around to start row 8 in the alkali metal column.